Okay, welcome class. This is class 5 of your 601 Quantitative Methods Business Research class. Recall we are not meeting in session today, class session. Instead, you are going to watch this video. I will be here directing through the slides. Unfortunately, this video is not going to get too high-tech, but I think it will work just fine. I'm going to go over slides that you can find on Blackboard, usual place under course material, class slides. You can print these out, follow along with me. So we're going to continue hypothesis testing for this video, and it's going to be an extension of the work we did in class 4, except this time we're going to add hypothesis tests for proportions, hypothesis tests for mean differences, and hypothesis test for proportion differences. Now it's all the same procedure, it's just a slightly different nuance when we get to how we conduct those tests. And the only real difference is the sampling distribution for each of these. In class 4 we learned, we used the sampling distribution of sample means to see how unlikely any particular outcome might be. Similarly, we're going to use the sample distribution for sample proportions to figure out how unlikely any proportion would be. Same thing for mean differences, same thing for proportion differences. Now I will say before we begin, you want to be clear and fluent on all of the class 4 material. You want to have a good understanding of hypothesis tests, good understanding of p-value, how we do the critical values. So I would, if you're not feeling great about that, I would go back and review that material before you watch this video. So work the homework problems for class 4, maybe even take the quiz, look at the answers to the quiz, make sure you're comfortable with how all of that works. And if you have to, you could even go back to the class 4 video and watch that again, because that is going to be key to your understanding of this material in this video in chapter 10 in class 5. So once you understand the class 4 material, this is going to be just easy, almost review, and just applying a few formulas. But if you are still a little shaky on hypothesis testing, the place for you to get unshaky is the class 4 material, class 4 quiz, class 4 homework, class 4 video. So I'm going to assume if you're still watching, you are comfortable with hypothesis testing and you're ready to move on to a couple different pieces. They are proportions, mean differences, and proportion differences. We're going to do hypothesis testing for those 3 things. And again, you can get the slides and print them out on Blackboard and follow along with me. In this video, I'm going to do a quick review of class 4, and then we're going to move on to hypothesis tests for population proportion, test for mean differences, test for differences between 2 population means, and hypothesis test for the difference between 2 population proportions. We're just going to add those 3 things in the video today. Alright, so the review, let's do a quick review of hypothesis testing, quick review of two-tailed test, quick review of p-value, quick review of one-tailed test. So hypothesis testing, let me skip to the last 2 bullet points here. In hypothesis testing, we will make a statement. We'll call that statement a null hypothesis. We will assume that to be true, and as we conduct our research, we will operate under the assumption that this null hypothesis is true. If we find overwhelming evidence to the contrary, we will reject this null hypothesis and we will accept what we call the alternative hypothesis, which is the opposite of what is stated in the null hypothesis. So if the null hypothesis is that the mean is equal to some value, the alternative is that it is not equal to some value. Also, we were looking at null hypotheses where the mean is greater than or equal to some value, which would mean the opposite would be that the mean is less than some value. So moving back up here, we make a statement called a hypothesis, and then if we produce sample results that would be highly unlikely under this assumption that the null is true, then we reject it and we conclude that it is false. Okay, so we call this null hypothesis the status quo, no change, and we're going to need compelling evidence to make a change, to say we reject it. This approach will usually involve a decision that will have to be made if the null hypothesis is rejected. For example, we might have a null hypothesis that a machine is functioning properly. Alternative, the machine is not functioning properly. So we're going to assume the machine is functioning properly. We're going to take some samples. If that comes out to be compelling evidence, overwhelming evidence, something that would be unlikely to happen under the assumption that the machine is functioning properly, then we're going to reject the null, accept the alternative. Alright, the way we set up these hypotheses, let me start over here with the two-tailed test. We might say a mean is equal to a certain amount, and the alternative is the mean is not equal to a certain amount. So we use the example, a realtor is telling us that the average rent is such and such. We said, we don't believe you, it could be high, it could be low. And we're going to set up an alternative hypothesis where what you say is not true. Now you recall for a two-tailed test starts with this equality, something equal to something else. And then there are two ways that could not be true. That could be, the mean could actually be much lower, or the mean could actually be much higher. So we're going to set up a rejection region in the lower and upper tail. We also looked at hypothesis tests. One-tailed hypothesis test where we're saying, all right, the mean is greater than a certain amount is our operating assumption of our null hypothesis. And then we said the alternative would be, no, the mean is less than some amount. So here we would set up a one-tailed test. We would say, all right, you say the mean is greater than or equal to this amount. All right, I'm going to assume that's true. All right, I'm going to say that's the mean equals whatever you say it is. But I'm going to set up a rejection region over on the lower tail and say, this is 5% of the time, 1% of the time, whatever. And if my sample mean falls in that range, I'm going to reject what you say and assume the alternative. And we could do one-tailed, upper tail, same sort of reasoning. Generalizing the testing procedure. So we'll state the null and alternative hypothesis. Think about what we're trying to test in step one. Choose a test statistic. What this means in the procedure is choose, are we using a Z statistic or a T statistic, were the two we looked at last time. And we choose a significance level for our test. So a significance level is our threshold for unlikely. So if we're going to say a 10% significance level, we say if it's less likely than 10%, we're going to reject your null hypothesis. And we just need to decide what level we're comfortable with. How confident do we need to be before we say, I think your assumption is wrong. Compute the value of the test statistic from your sample data. So we're going to go out and get some sample data to prove or disprove the null hypothesis, or, to test the null hypothesis. I shouldn't say prove or disprove, just to test it. And then we're going to see how many standard deviations above or below the mean our test statistic is, given the assumption of a true null hypothesis. And then we're going to apply the decision rule and make the decision. And our decision rule can be made one of two ways. One way is our critical value region, critical value version. In that case we said, well, If, depending on our significance level, we're going to find a z-value that represents the cutoff for our rejection region. So we're going to find the 5% of the data in the upper tail, 5% of the data in the lower tail. If we're looking at a z-distribution, that would be 1.65 positive, 1.65 negative, and if our test statistic is outside of that, meaning greater than 1.5 or less than negative 1.65, we reject. We could also use the p-value version. Now, the significance level is our threshold for what we would believe for unlikely behavior. The p-value is the exact calculation for our test statistic, exactly how unlikely. So the significance level might be 10%, so anything less likely than 10% we reject. And our p-value tells us exactly how much less than 10% it is, or it could be greater than 10%, and we wouldn't reject. And for the p-value, you find the test statistic, you find the area under the curve associated with that test statistic, and for a two-tailed test you need to double it, because when you start a two-tailed test you don't know if the sample statistic is going to be high or low. So we're saying let's find the probability of getting something at least that extreme on either high or low. And for a one-tailed test, you do not need to double the p-value. Or you do not need to double that area under the curve to get the actual p-value. Okay, so that's that. Alright, and then I guess we've kind of already pre-reviewed this, but we're going to review again. Two-tailed test starts with inequality. You say the mean is equal to some amount. Alternative, no, it's not equal to some amount. There are two ways we could disprove that. We could get sample data that is really, really high or really, really low, in which case both cases we would reject the null. So, level of significance. If suppose it's 10%, we divide that by 2 and put 5% in each tail. Find the critical value, and if it was 5%, it would be negative 1.65, positive 1.65, and we would calculate our test statistic, which I will review on the next slide. So let me actually just do that right now. Okay, so let's turn to the next slide. So suppose we're doing a sample mean, and we're calculating our test statistic. We're using the z-distribution, so we'll call it a z-statistic. We take our sample mean that we collected when we were trying to figure out whether or not to believe you. We find the difference between that and what you say the true population mean is, and we divide by the standard deviation of the sampling distribution of the sample mean. So this tells us how unlikely our test statistic is, specifically how many standard deviations it is above the mean. And you will recall that the standard deviation of the sampling distribution of the sample mean is the population mean divided by the square root of n. Alright, so we've got our z-stat. Let me go back to the previous slide. Once we have our z-stat, we can find our p-value. We look under the normal table and find the area under the curve associated with that z-stat. For a two-tailed test, multiply that by 2. And we apply either rejection rule. Alright, is our z-stat more extreme than the positive and negative critical values? These two lines mean absolute value, so yeah, they're just saying, is it more extreme on the negative side, more extreme on the positive side? Absolute value just means the distance from 0. Or we use the p-value version. If the p-value, the probability, exact probability of this test statistic is less than our significance level, which was our threshold for unlikely, then we reject the null hypothesis. Alrighty. We already went over test statistic. All right, and this is the graphical illustration of this. Now this is, if it's sampling, I'm going to abbreviate this, sampling distribution of the sample mean. All right, this is the great thing we have that makes so much of what we do in this class possible. This is a frequency distribution of every sample mean. And we know, because it's normally distributed, that the means are going to fall in a certain manner. Right? The percentage of the data is going to be a predictable number of standard deviations away from the mean, the center of this distribution. And if we have a rejection region, we can quantify, say 5% of the data in the upper tail, 5% of the data in the lower tail. We can quantify that with a specific z-value. We're using 1.65 for the cutoff between the upper 5% and the bottom 95%. Also, negative 1.65 is the cutoff between the bottom 5% and the upper 90%. So if our test statistic lands in that rejection region, we reject the null hypothesis. All right, next slide, we have a definition of p-value. You've heard me say it a number of times. I'll read it once more. P-value measures the probability that if the null hypothesis is true, we would randomly produce a sample result at least as unlikely as the sample result we produce. Okay, fine. Find the area under the curve. And if it's a two-tailed test, double it. If it's a one-tailed test, don't double it. And we can apply the p-value decision rule as we have discussed. All right, so we're continuing to review. Now we're just doing a review of a one-tailed test. I have a few scribbles on here as I was preparing. Let me remove this, one of the scribbles anyway. Alright, so for one-tailed test, there's only one way we could disprove a null hypothesis. So, alright, faked you out. Let me put my scribble back on here. So suppose we have a null hypothesis that the mean is less than $20. Like the average amount customers spend at the concession stand is less than $20. Oh wait, greater than. Okay, now I'm trying to like prove, I want more funding or something for my concessions. I'm like, oh, the customers spend more than $20. So you look at that and you say, well, I think they actually spend less. And I'm going to find evidence for that. I'm going to see if I can find evidence for that. And if I do find that evidence, I'm going to reject your null hypothesis that the mean is greater, and I'm going to accept the alternative that the mean is less than $20. So, alright, so let's look at, sometimes, I haven't really talked about this too much, but sometimes I will put underneath the normal distribution graph, I will put the actual numbers and the z-values, z-numbers. I'll say z-values. Okay, so the actual number was 20 for my null hypothesis, my mean, my supposed mean. I'm saying it's 20, maybe it's high as 22, you know, it's at least 20. Let me actually, I'm going to erase that 22 because the only important number here is the null hypothesis of 20. You, in your attempt to verify this information, you're going to say, well, what is our critical value if we want a 5% significance level? That's our threshold for unlikely. We're going to choose a critical value of negative 1.65. If we find sample data that is more than 1.65 standard deviations below the mean, your mean of 20, then, or my mean of 20, then we're going to reject the null hypothesis. So, sorry if this is confusing, but what I was trying to do here is, say we've got our so say we come up with a sample mean of $14. Okay, so we've got our sample mean of $14, and you say, well, wow, that's significantly less than $20. Is it enough less than $20 to reject your null hypothesis? Well, we're going to need to find out. So we're going to need to crunch that test statistic, that $14, find out how many standard deviations it is below the mean. And if it is more than 1.65 standard deviations below the mean, we're going to reject the null hypothesis. Okay, so I don't know if this attempt was successful, but what I wanted to do is just draw your attention to, we have the z-values, which is standardized. The mean of any z distribution is 0. And we know that below 1.65 standard deviations on any normal distribution, there will be 5% of the data. We also have our real numbers, the $20 concession, and our $14 mean sample mean. And there's of course a sample size and a population standard deviation that I did not include on this. Okay, so that was a quick review of a one-tailed test. We could do the same thing on a upper tail, and it would just be the different statement. The null hypothesis, the alternative hypothesis would be flipped around, and we would have a rejection region in the upper tail. Alright, so that is a quick review of class 4. We're going to move on now to the real material for class 5. Okay, so for the new material for class 5, the first thing we're going to do is a hypothesis test for a population proportion. Let me start with the two-tailed test. This is just like we did with means. Suppose we have a null hypothesis that the population mean is equal to some amount. Okay, suppose you might say the percentage of people who support Donald Trump is 44%. And I say, well, I don't think you're doing great research, whatever. I just want to, or maybe I'm just doing this as an exercise. I'm not trying to get into an argument with you. I'm just trying to find evidence and quantify how I'm making this decision. So I set up an alternative hypothesis that the population proportion is not equal to that amount that you say. Again, looking for overwhelming evidence in the upper tail or the lower tail. Similarly, I could say the population proportion is less than some amount, like less than 30%. I think less than 30% of people would support this change. Alternative hypothesis would be more than 30% of people would support this change. We could do a hypothesis in the just the different tail hypothesis, a different one tail hypothesis. You might say null hypothesis. I think less than 15% of students at Mercy College live on campus. Actually, it'd be pretty easy to get the exact numbers, so maybe that's not a good example. So I think less than 15% of students at Mercy College are baseball fans. And the alternative would be that more than 15% are baseball fans. So we would set up a one-tailed test to test this proportion, this population proportion. We would use the same thing we use for means, testing means, and the same thing we've used for a number of classes, the sampling distribution of sample proportions. This is this wonderful normal distribution. It is a frequency distribution of all the sample proportions. We know that this is normal, and because it's normal, we know where the data lies in terms of how far above and below the mean it is. And if we use good sampling procedures and we have the appropriate sample size, this distribution will be approximately normal. And recall that as long as the sample size times the population proportion is greater than or equal to 5, or the opposite, n times 1 minus the population proportion is greater than or equal to 5, then we're good. And we know two important things about this normal distribution. One, it is centered around the true population proportion, and it has a standard deviation based on the math of how close the population proportion is to 50%. If it's closer than 50%, then it's going to have a wider standard deviation. If it's more extreme, it's going to have a tighter standard deviation. So what we'll do in hypothesis testing is we will assume that your statement about 44% of people are supporting Donald Trump, we'll assume that that's true. Then we'll go out, we'll get some sample data, and we'll see if our sample data provides overwhelming evidence to the contrary. Pretty straightforward, pretty similar to what we did last time. And the way we'll calculate our test statistic for a population proportion is we will look at the difference between our sample proportion, this p with a bar above it, and the population proportion. All right, how much of a difference did we find in our sample versus what you say under the null hypothesis? We'll calculate how many standard deviations above and below the assumed mean that would be. So this is the standard deviation. If you just look on the previous slide, this is the standard deviation of the sample distribution of sample proportion. And that calculation gives us our z statistic. And then we will see, all right, does this z statistic fall in a region in which we would say that is so unlikely under the assumption that 44% of people support Donald Trump that I'm going to reject your null hypothesis and I'm going to assume the alternative hypothesis. Alright, so I actually wrote down a little start of an example here, but I think I'm going to leave it at that because we're going to do an example in a minute. So we've got z-stats, and on this next slide we've got the rejection rule. We're going to set up the critical values the same way for a population proportion. And let's go straight to our two-tailed test. If our null hypothesis is that the population proportion equals a certain amount, say 44% of people support Donald Trump, if the absolute value of the z statistic we calculate is greater than the critical values we come up with based on whatever significance level we are comfortable with, then we're going to reject that null hypothesis. And we can set up a one-tailed test or a two-tailed test the exact same way we set up the sample mean tests. We can reject based on whether or not this test statistic falls outside or in the rejection region. We can also use the p-value approach. We calculate the p-value the exact same way we calculated the p-value for sample means. We would calculate our test statistic. We would see on the z-table the area under the curve associated with that test statistic. If it's a two-tailed test, we double that number and we get the p-value. If it's just a one-tailed test, we do not double that value. That value is our p-value. And if the p-value is less than our significance level, which would be our threshold for what we believe to be unlikely, then we reject the null hypothesis. All right, let's move on to an example, or not move on. I don't want you to think we're moving too fast through this material. We're actually going to do an example which will sum up everything we just went over with the hypothesis test for proportions. Alright, so we are looking at an example for a hypothesis test for a proportion, and we're going to look at page 356, number 10. I'm going to set this to the side. I'm going to pull out my textbook. I will read this to you. You may not be able to see it in the video, but you can read along with your textbook at home. So the question says, in the past, years, at least 20% of students at State U chose to pursue public service careers after graduation. For an editorial piece on declining student commitment to public service, the school newspaper surveyed a simple random sample of 100 currently enrolled students and found that only 12 of them expressed an interest in a career in public service. So, past years, the assumption is 20% of students go into public service, but now we have evidence that maybe less than 20% go into public service. So let's keep reading. Does this sample result provide statistical evidence of a decline in student commitment for the population of students currently enrolled at State U? That is, can the sample result be used to reject a population proportion greater than or equal to 20 null hypothesis? Use a significance level of 5%. Show the null and alternative. Based on your sample results, should you reject the null? Alright, let's do it. So, let me pull out a piece of paper here. I'll try to write big. Alright, so we've got a null hypothesis that says this population mean of all students at State U who want to go into public service is greater than or equal to 20%, 0.20. We're going to assume that's true, and we're going to gather some evidence to see if we find that that's not true. So our alternative hypothesis would be that the population proportion of students who want to go into public service is less than 20%. Alright, we had a sample proportion of 12%. Alright, we asked 100 students, 12 of them said we're going into public service. So that's a good sample size. Assume we use proper sampling procedures. N equals 100. Okay, we at some point are going to need to find the standard deviation of the sampling distribution of sample proportions, but we'll hold off on that for just 1 second. Let's go ahead and draw a normal distribution and think about how we're going to visualize this. So this is sampling distribution of sample proportions. Sampling distribution of sample proportions. We're going to assume, based on the null hypothesis, that the mean, the true population proportion equals 20%. And we're going to think about how we would assess information to the contrary. So the null hypothesis is the mean is greater than 20%. So if we went out and found a sample greater than 20%, we're like, all right, fine. You said greater than 20%. It's greater than 20% based on our sample. Where we're going to be concerned is if we find a sample proportion less than 20%, and in fact significantly less than 20%. And I guess I forgot to put the confidence or significance level here, so I'll put it now. Significance level, I believe, is 0.5%. Yes. 0.5. So we're looking for the 5% of the time, alright, that we would get a really low sample mean. And we're going to say, well, under your assumption, the sample, I keep saying sample mean, I'm sorry, but sample proportion. Under your assumption that the proportion is truly 20%, we're going to look for a result that would only happen 5% of the time. And if it happens, we fall into that 5% of the time, we're going to say that's so unlikely that we would rather say your assumption is incorrect than say that that happened by chance. So we'll call this our rejection region. Alright, so let's find the critical value, the z-value, associated with that rejection region. It's going to be the z-value that separates the bottom 5% of the data from the top 95% of the data in any normal distribution. And we know that number to be 1.65. If you were to look on your z-table, you would see or excuse me, negative 1.65, you would see that the negative 1.65 has the area under the curve of 5%, meaning it separates the bottom 5% from the top 95%. So we're going to be looking for a test statistic for this sample proportion of less than negative 1.65. If it is less than that, we're going to reject the null and assume the alternative. Okay, well, let's go ahead then and calculate our standard deviation of our sampling distribution of sample proportions. Now, if you recall from, I think, a couple slides ago, the proportion we're going to use to calculate this is the assumed population proportion under the null hypothesis. It's the 20%. We're not going to use the 12% to calculate standard deviation. We're going to assume what they say is true, or assume the assumption is true, and we're going to see what would the standard deviation be under that assumption. And if it falls in that 5% under that assumption, then we're going to say not true. So let's calculate our standard error. It's going to be our 0.2 times 1 minus 0.2, which is 0.8, divided by 100, square root of that whole mess. Alright. Pull out the calculator. Let's go 0.2, enter 0.8 times 100 divided by square root that, and we're going to get 0.04. 0.04, alright, a nice even 4%. We like that. So now let's calculate our test statistic. Find out how many of these standard errors this sample proportion is below the assumed population proportion under the null hypothesis. So let's get our z-stat, to calculate our z-stat rather. 0.12 minus 0.2. Alright, that's the difference between our sample proportion and the assumed proportion under the null hypothesis. Divide by the standard error, 0.04, equals, check it out, 2 minus 0.04 divided by negative 2. Okay, so we've got a z-stat of negative 2. Alright, negative 2 falls here. Alright, this is negative 1.65, this is negative 2. This is outside past the threshold for our rejection region. So we know right off, or not right off, I guess we've been working for a while, we know right now that we're going to reject. I'm going to put an arrow here, reject, exclamation point. Now, just for fun, let's calculate the p-value associated with a z-stat of negative 2. So our p-value gives us more exact information about exactly how likely it would be to get a test statistic of negative 2. We know it's less likely than 5% because it's past negative 1.65, but let's find out exactly. Alrighty, let's look in the Z table. Negative 2.00 is 0.0228. Alright, 0.0228. Since this is a one-tail test, we do not need to double this. We just say our p-value is 0.0228, which is about 2.3%. There's a 2.3% chance of getting something this unlikely if the assumption of 20% is true. So we're going to reject the null hypothesis, assume the alternative, that the true population proportion of students who want to go into public service is less than 20%. Let's double check and make sure that answer jives with the back of the book. Chapter 10, number 10. Okay, z-stat is -2, critical value is -1.65, reject, p-value 0.0228, reject. Alright, we're good. We're rocking and rolling. We're going to move on now to the next thing, which is hypothesis testing for mean differences. Okay, so here we are with our second topic, the tests for the difference between two population means. This independent samples, that's just, we don't need to worry about that. Just if you notice, if you look in your textbook, that's different from what the textbook calls matched samples. So it's just two population means, the same way we've studied population means 2 classes ago. And we're just going to impose the hypothesis testing techniques on population means, or differences between them rather. So let's go straight to this two-tailed equality test. So suppose we have a null hypothesis that population mean 1 minus population mean 2 equals 0. So that is a null hypothesis that there is no difference between these two populations. So suppose the mean income in town 1 minus the mean income in town 2, guess what? They're exactly the same, and that means that the difference between them equals 0. If we're trying to investigate whether or not that's true, we might pose a hypothesis test, as that is the null hypothesis, and we look for overwhelming evidence to the contrary and say, well, the difference between them is not equal 0. So the difference could be a significant high number or a significant low number. And we would construct our two-tailed test based on what we consider a good threshold for unlikely, also known as our significance level, and we would see if a test statistic fell in that unlikely region. If it did, we would reject the null hypothesis and say that the difference between them does not equal 0. Now, we could, and instead of saying 0, just a note, we in this class we will always use 0, but just to put this in context for you, we could say the difference is 5 or the difference is 6,000. That could be our null hypothesis, that the difference between these two means is $15,000. We think that's what it is. And we are going to test whether or not we have enough information to reject that difference of 15, suppose. So we will always use 0, and that will just mean 0 difference, no difference. In other words, the population means are the same. But you could put in any number you want for 0. Okay, and then one-tailed tests would be some sort of assumption. Let's go with this number 2, because I think that's going to be easier to understand. This null hypothesis, the population mean 1 minus population mean 2 is greater than or equal to 0. So that means it's a positive number. So income in town 1, we think it's 70,000. Income in town 2, we think it's less than that. Maybe it's 69,000, maybe it's 50,000. So that would leave, whatever. So if this was 70 and this was 59, that would mean 11,000 would be the answer to this. Population 1 minus population 2 would equal 11,000, and that would be greater than 0. And what we're saying is, we think the population mean in town 1 is higher than the population in town 2. That's all we're saying by this 1 minus 2 is greater than 0. So we might think that. Someone else might say, well, let's set up a hypothesis test to see if we can disprove that, and then we just flip the sign. We say that that is less than 0. That if we take population mean 1, subtract population mean 2, we're going to get a negative number, meaning, in fact, the average income in town 2 might be bigger than the average income in town 1. So the bigger number minus the smaller number would be less than 0. So, and it's the same way we would say, you know, we're going to operate under the assumption that the null hypothesis is true. The alternative hypothesis is the opposite of that, and we're going to see if we find overwhelming evidence to disprove the null. And finally, so this, if we want to set up the test, the population mean in town 1 minus the population mean in town 2 is less than 0. We might be saying, hey, you know, this town has a lower income than town 2. All the poor people live in town 1. All the rich people live in town 2. So when you take the average income in town 1 minus average income in town 2, you're going to get a negative number. And then someone comes along and says, wait a minute, no, that's not true. I think it's the other way around. So let's look for evidence and see if we can disprove your null hypothesis. The z-statistics are going to be set up the same way. If it's a one-tailed test, there's going to be the z-critical values, well, both. The z-statistics and the z-critical values are going to be set up the same way. And if it's the z-stat falls in the rejection region, we reject. P-value approach, same way as well. If it's a one-tailed test, we're going to find the area under the curve associated with that z-stat, and we're going to double it. If it's if it's two-tailed, I don't remember what I said. But let me just repeat that again. If it's a two-tailed test, we find the area under the curve and double it. If it's a one-tailed test, we find the area under the curve and we do not have to double it. Same rationale, same logic as before. Okay, now what is going to change is just the way we calculate our z-stat, because we have a slightly different standard deviation metric. So let's move on to that. All right, so if we're calculating mean differences, the key tool is going to be our sampling distribution of the sample mean difference. We take the difference between town 1 income, difference between average income and town 2. We do that 10,000 times. We put it all in a frequency distribution. You are going to get this sampling distribution of sample means. And God be praised, that is going to be normal. And when I say God be praised, I'm not saying anything religious. I'm just saying we are happy about that, because if it is normal, we can make all sorts of assumptions about what the data will look like. So the sampling distribution of the sample mean has a mean which mirrors the true population mean difference. All right, we're most likely going to get the actual difference between town 1 and town 2. And it's going to have a standard deviation, which we can calculate based on the standard deviation of the population in town 1, population in town 2, and divide by sample size. So the bigger sample size, the tighter this distribution is going to be. So we're going to calculate our test statistic using our sample data, when we sample from town 1 and town 2, and this standard error figure. All right. Suppose we're setting up a two-tailed test. This is our sampling distribution of the sample mean difference. Suppose we were looking at a significance level of 5% in this example. Significance level 0.05. And it's a two-tailed test, so we start with some inequality. There's some equality. And that the difference between population 1 and mean and population 2 equals 0. It could be disproved one of two ways. It could be, our sample could be really high or really, really low. And we would have 2.5% in either tail. If we have 5% in either tail, we have 1.96 plus or minus as our critical values for our rejection region. Alrighty. Now, how do we calculate our test statistic to determine whether or not that test statistic falls in the rejection region? Well, the first thing, we go out and we take some sample data. Sample data, this is sample mean from town 1, this is sample mean from town 2. We find the difference between those two. And then we subtract off 0 because, as you recall, in all of the tests we use in this class is we're going to use a null hypothesis that the difference is equal to 0 or the difference is greater than 0 or less than 0. We could use other numbers. I gave the example, we want to test a null hypothesis that the difference is 15,000. So we could put 15,000 there if we wanted to, but for our purposes, as we get used to this, we're just going to say the difference is 0. So let's see. So we're going to find out how different. So if this difference, all right, so this is town 1, this is town 2. So we do a sample of town 1 and we get, say, I don't know, 70,000 for income. And we get town 2 and we get, say, 59,000. The difference between that is 11,000. And we want to find out how many standard deviations 11,000 is above the mean that we would expect under the assumption that your null hypothesis is true. And then this minus 0 because we're just saying how different is it from 0. Okay, so this is our sample data. This is based on our null hypothesis of saying 0 difference. And then we divide by the standard deviation of the sampling distribution of sample mean differences. And we know that formula. Okay. All right, now, since we do not necessarily have the population standard deviation all the time, when population standard deviations are unknown, we theoretically do two things. One, we substitute in the sample standard deviation. The other thing we might do is use the t-statistic. And as I mentioned when we did mean differences the first time, I said you could use the t-statistic. You could use that slightly higher numbers that are associated with the t-statistic to add a little extra padding. But statisticians are comfortable with using the z-table when we do mean differences. And the reason for that is because there's just more moving parts. They say, all right, look, as long as we have a sample of 30 from population 1, a sample of 30 from population 2, maybe they're going to be a little bit off, but there's more numbers involved, and there's a greater chance that any abnormalities are going to cancel each other out. So we in the case where we do mean differences, both when we're just doing mean differences for trying to calculate a confidence interval for mean differences, and now that we're doing hypothesis testing for mean differences, we're good with using the z-statistic. So to get the sample standard deviation of the sampling distribution of the sample mean difference, or standard error of the sampling distribution of the sample mean difference, we substitute in our sample standard deviation for population 1, population 2, sample size 1, sample size 2, and we take the difference and our mean differences and we divide that by the number of standard deviations that we calculate. All right. Let's do an example. Okay, so we're doing an example for our test for the difference between two population means, and that example is going to be page 362, number 24. So 362, number 24, let me set that to the side. Go ahead and pull out your book and you can read along with me. So for number 24, in an agricultural study done to examine the impact of using new mixed pesticides on Canadian canola crop, the Canadian canola crop, a sample of 459 farms using a new pesticide mix and a sample of 250 295 farms using a conventional pesticide mix were randomly selected. The average revenue per acre in the sample of new mix farms was $181.90. The average revenue per acre for the sample of conventional mix farms was $152.10. So we're getting more revenue when we use this new mix. Is that enough to say we have a statistically significant difference? And could we reject, suppose, a null hypothesis that there was no difference between them, or that the old was even better? Well, let's see what they're asking us to do. Construct a one-tailed hypothesis test to determine if these sample results are sufficient to reject a null hypothesis that the average gross revenue for the new mixed farms is no greater than the average gross revenue for conventional mixed farms. Use a 5% significance level, and guess what? We know the population standard deviations from the new mixed farms and the old mixed farms. Alright, so let me put this off here. Let me pull out a piece of paper and we'll start calculating this problem. So let's look over here at our new data, and let's look at it here, over here on this side for our old. Alright, so new, old. Alright, so we got, for the new mix, we got a sample mean equal to 180, 90. For the old, we got a sample mean equal to 152.10. Alright, let's see here. So in the new mix, we sampled 459 farms. In our old mix, we sampled 295 farms. Alright, I'm going to move this book out of the way. Okay, what else do we know? Fortunately for this one, we know population standard deviation, so that makes it just a little bit easier for us. The population standard deviation for the farms using the old mix was that 75/20. Alright, so let's set up our null and our alternative hypothesis. So they're telling us a one-tailed test. Okay, so we know it's a one-tailed test. To determine if these sample results are sufficient to reject a null hypothesis, the average gross revenue for new mixed farms is no greater than the average gross revenue for conventional. So this is going to be a tiny bit tricky. So what I want to do is I want to go back to slide 20 for one moment. We're going to look at these different options we have for setting up hypothesis testing. So we're looking at our one-tailed test options. Now, what we ultimately might be trying to prove is that the average revenue for the new mixed farms is greater than the average revenue for the old mixed farms. So let's look at this first column here. This mean 1 minus mean 2 is greater than 0. That might be what we're trying to ultimately prove with this new mix. So the revenue, average revenue for the new mix minus the average revenue for the old mix is greater than 0. All right, it's some number more than 0. It's positive, meaning that there's more revenue in the new generated from the new mix than the old mix. And it's definitely not negative. So let's make this our alternative hypothesis, and then let's make this our null hypothesis. This would be that the revenue from the new mixed farms minus the revenue from the old mixed farms would be less than or equal to 0. So it would be a negative number, meaning that the old mix is actually making more. And that's going to work with what we're instructed to do, because it's a one-tailed hypothesis test, to see if we can reject a null that the average gross revenue for new mix is no greater, all right, So it's no greater. So it's either equal to or less than. That is our null hypothesis. No greater. That the average revenue for the new mix is equal to or less than old mix. So let me put my worksheet back here. So our null hypothesis is going to be mu1 minus mu2 less than or equal to 0. And our alternative hypothesis is mu1 minus mu2 is greater than 0. So this is really where the rubber meets the road here. We're going to say that the average for new is, and if you take the average from new and subtract off average to old, that leaves us a positive number, something greater than 0. And we're going to see if we have overwhelming evidence to confirm that. And it could be a little confusing the way we had to phrase it in order to set up our test like that. But you just go ahead and if you want to review that, maybe pause the tape, think that through, rewind if necessary. We're not saying anything complicated. We just have to phrase it in a way that sounds a little tedious. Alrighty, so we've got our null and alternative hypothesis, and we're looking at a significance level of 0.05. Alright, let's draw a little bell distribution, a little normal distribution. Alright, we've got our sampling distribution of sample mean differences. And what we're going to do, we're going to assume our mean difference is 0. Alright, so our mean 1 minus mean 2, we're gonna do the equals part 0 here. And we're going to say it's equal to 0. And I know this is confusing. We're saying this is equal to 0, and here we're doing a greater than, less than. But just for purposes of analyzing this graph, we're going to say this equals 0. And if it is less than 0, we are not going to worry. But if it is, and if it's right equal to 0, we're not going to worry either. But if it is greater than 0, then we're going to say, well, wait a minute. Maybe we're going to need to reject this null and assume the alternative. So this mean 1 minus mean 2, if it comes out to a number greater than 0, it's going to be somewhere in the upper tail. If that number is significantly greater than 0, meaning it falls in the only 5% likely, then we are going to reject the null and assume the alternative. Okay, so be sure you're comfortable with how we set that up. I don't want to explain it again because I'm going to get it wrong if I do. So just rewind the tape if necessary and make sure you're clear on how we set up the alternative and the null, and clear that we're using a one-tailed test, even though we just, for the time being, when we set up this normal distribution, we have to say the mean is going to be that the difference is 0, and we're looking for an unusually high difference. Okay, so we need a critical value for this, 5%. All right, the cutoff that separates the upper 5% from the bottom 95% is a z of 1.65. Good, we've got that. So let's find our test statistic. In order to find our test statistic, the key thing we're going to need is the standard deviation of the sampling distribution of sample mean differences. And we learned that, I think, a couple classes ago. So standard standard deviation, mean 1 minus sample mean 2 equals. All right, so I believe it's going to be the 83.4 squared divided by sample size 459 plus 75.2 squared divided by the sample size of that. And we're going to square root that whole thing. Okay, so we've got standard deviation population 1 squared divided by sample size population 1, standard deviation sample 2 squared divided by divided by sample size population 2, square root the whole thing. All right, and then that's going to get us one step closer to our test statistic. So let me crunch that. All right, 83.4 squared 459 divided by 75.2 squared 295 divided by plus square root that whole thing. I'm coming out to 5.856. Alright, now I'm going to store that number in my calculator because I'm going to use that for a calculation in a moment. Store 1, enter. Alright, so to calculate the test statistic, the z-stat, I need to, so I need to calculate the mean difference that I found. So 181.9 minus 152.1. Alright, that. And then we're doing minus 0. So we're saying this doesn't have to be 0, it could be 5. We could say, well, let's test to see whether the difference is 5, but right now we're just testing to see if the difference is 0. So we're subtracting 0 from that, and we're going to divide by our standard error, 0.856. We'll see what this comes out to. So 181.9, enter, 152.1 minus, recall that number, divided by, okay, jeepers creepers, that comes out to 5.086. Okay, good God. So that is 5 standard deviations above the mean. Okay, so that is off the charts. So if we look at the z distribution, it only goes up to 3. So we know that this is an extremely significant, extremely unlikely, under the assumption of no difference, test statistic. So our critical value was 1.65. And the value we actually got, right here, 1.65, and the value we actually got was 5.09. Whoa, jeepers. All right, so we're going to reject for sure. Now, if we wanted the p-value here for this, as I said, this 5.09 is off the charts. So let's look at it, the highest, excuse me, let's look at the highest one we have. Oh gosh. So a z of 3.09, our test statistic, we're going to say there's of 3.09, there would be 0.001, so it would be 0.1% of the sample means would fall in that area under the curve. So if we had gotten, instead of 5.09, if we had gotten 3.09, which is the highest your textbook goes up to, there would be a 0.1% chance of that happening. So there's even a less than 0.1% chance of this happening. So it's like, I don't know, so p-value is like, say, close to 0. Say close to 0. Or we could say less than 0.001. Okay, so for that reason we're going to reject, because remember our threshold was 5%, and we have a percentage of this happening extremely close to 0. Now it's not 0, there is a possibility that there could be in reality no difference between the new revenue and the old revenue if we sample the whole population, but there would be a much less than 0.1% chance of us getting these numbers if there was truly no difference. Alright, so let's check in the back of the book. Fingers crossed to make sure we got that right. When I say we, I mean I. Chapter 1024, I believe. Okay. So yeah, we get the sample mean of 5.856. We got the z-stat of 5.09. Jeepers, critical value of 1.56, and we reject because the p-value is so close to 0. All right. So that is your example for the mean differences. So let's move on to the next piece, the next topic, which I believe is proportion differences. Alrighty, so here we are with the last topic, test for differences between two population proportions. Let me go straight to the two-tailed test. Suppose someone tells us that there's no difference between one population proportion and the other population proportion, so when we subtract one from the other we get 0. And we're like, I think those two are different, or I don't trust you, or let me just not necessarily be argumentative, let me just set up a good scientific test to see if I can find overwhelming evidence that in fact there is a difference. So maybe someone says, all right, the proportion of men who support Donald Trump is the same as proportion of women who support Donald Trump. So in that case, the proportion of men minus the proportion of women would be 0, or close to 0. And we would set up an alternative hypothesis, which would be the opposite of that. The proportion of men minus proportion of women would be not 0. There are two ways we could disprove this null hypothesis if we find a really high positive number or a really high negative number. So that would be a two-tailed test. If we were looking to prove or disprove something a little more specific, if someone maybe said, hey, I think the proportion of men who support Donald Trump is significantly greater than the percentage of women who support Donald Trump. So if we take proportion men who support Donald Trump minus proportion women who support Donald Trump, we're going to get a number greater than 0. It's going to be a positive number. So we would set up a hypothesis, null hypothesis, with the opposite of that. We would say proportion of men minus proportion of women is either 0 or less than 0. And if we find overwhelming evidence that this is positive, then we could reject the null hypothesis and assume the alternative hypothesis. So in that case, if we're trying to say something specific, prove something specific, we could use the one-tail test. If we're trying to say or prove the other direction, we could use a one-tailed test, the other side. And then as I started saying, if we didn't know, or we didn't want to get specific in our first question, we would leave open the possibility that we could disprove the null hypothesis either with a really high positive or really high negative number. So everything is the same as with all the other hypothesis testing. We can use a critical value approach. For the difference between two population proportions, we use the z-distribution. We're good with that. And if our test statistic is outside the critical value, then we reject. We could also use the p-value approach. We'll get our test statistic. We'll see the area under the curve associated with that test statistic. For a two-tailed test, we'll double it. For a one-tailed test, we will not double it. And we will reject if the p-value is lower than our significance level. All right. So the key to all of this, as you might have guessed, is the sampling distribution of sample proportion differences. So this is a proportion difference, all right? This is proportion of men who support Donald Trump. This is proportion of women who support Donald Trump. If we were to do that same sample 10,000 times, we put it on this distribution, it comes out to this beautiful bell curve. The mean of that distribution is the actual difference, like maybe it's 6%. Maybe in reality 6% more men support Donald Trump than women support Donald Trump. That would be the mean and would have a standard deviation based on how close these proportions are to 50%. Yes. It would have a standard deviation that statisticians have used or constructed for us when we're combining two populations. Okay, and this distribution is normal as long as we use good sampling size, and the standard deviation is, as we learned a couple classes ago, this formula right here. All right. And we're going to use the same principles, the same rejection, same don't reject type of thing. This would be a one-tailed test with 5% of the data in the upper tail. We would say, well, if there truly is no difference between proportion 1 and proportion 2, then we would only get a sample proportion difference this significant 5% of the time. Same thing. If the null hypothesis is true, then this would only happen 5% of the time. And when I say this, I mean the sample proportions that we go out and test using good sampling techniques, and we find the difference between those two. Alrighty. And then we're going to get our test statistic. It's the same subtract 0 principle here. We're going to say our sample proportion 1 minus sample proportion 2. So we go out and we sample men, say, do you like Donald Trump? We go out and sample women, say, do you like Donald Trump? And we find a difference. We find the difference of men is 6% greater. So 6% is the difference. And we subtract 0 because we're using a no difference question. Just as I mentioned in earlier examples, we could put something other than 0 in, and we could test. We could say, you know what, I think the difference is exactly 4%. And I'm going to test to see if that's true, in which case I would subtract off 4 and see how far off I am. But for now, we're just taking the difference, assuming no difference, so we're subtracting off 0. So sorry if that gets a little confusing. We're first taking the difference between the sample proportions, and then we're saying, well, if we're going to do a no difference hypothesis, then we subtract off 0, and we simply see how many standard deviations this proportion difference is above the mean. So we divide by the standard deviation of the sampling distribution of sample proportion differences. And I believe on the next slide, this part, the standard error is filled out a little bit more. Or no, it's not. Okay, so we don't have it. We had this in the previous slide. It's that big long formula. Just make a note of it. Turn back to the previous slide, say star. That's the formula we're going to need to use when we calculate the standard error. The thing I need to talk about now is what we use for the standard error. When we're calculating this standard error, I guess we do have it. We have it down here. This is the standard deviation for the sampling distribution of the sample proportion differences. And you will see we've got this sample proportion pooled here. What that means is we are going to combine the proportions we get for the two samples. So if we ask, we take the proportion of men who support Donald Trump, we take the proportion of women who support Donald Trump, and we do a weighted average of those. And that's going to be our pooled sample proportion that is going to help us find the standard error. And one above here, this formula here is just a weighted average formula. So, all right, number of men we ask times the number of men who support Donald Trump plus number of women we ask times the percentage of women who support Donald Trump divided by the total number of people we asked is going to give us our weighted average for sample proportion. So that's a little nuance that may trip you up. You're going to need to calculate the weighted average for the two sample proportions when you're calculating the standard error. One more time, you're going to need to calculate the weighted average of the two sample proportions when you are calculating the standard error. All right, if we're in class, I would say ask if there's any questions, but I'm going to assume there's not. And we are going to do an example to make sure we're clear on this. Page 373, number 38. All right, so here we are, if I can get this focused. We are doing our example for the test for the difference between two population proportions. And we're going to do an example, page 373, number 38. Why does that keep getting blurry? I don't know. Something weird is happening. Oh, perfect. All right. So, page 373, number 38. Let's put this to the side. And let me read this to you. You can read along with me. So, based on home ownership, on its home ownership survey, Home Mortgage Giant Fannie Mae reports significant differences in home buying knowledge between demographic groups. In a random sample of 236 college-educated adults and 259 high school-educated adults, the survey found that 65% of those in the college sample and 60% of those in the high school sample were aware that a mortgage does not require a 30-year commitment. Whew, boy, that was a mouthful. So, essentially, more of the college-educated adults knew this little detail that a mortgage does not require a 30-year commitment. And 5% fewer of the high school-educated adults knew that same thing. So with regard to this particular knowledge issue, can these sample results be used to reject a no difference in population proportions? Null hypothesis for the two populations represented. Use a significance level of 5%. Okay, so we see the word no difference. And I may have been using that word a little too freely, but no difference might be a clue that we're doing a two-tailed equality hypothesis test. The other clue that we're doing a two-tailed test is we don't see any statements about less than or more than. So in absence of statements about less than or more than, we can think that this is probably a two-tailed test. We're just going to see, is there a difference between these two demographic groups? And that difference could be either really high or really low. But since we already have the numbers, we kind of know where we're going with this. So let's set up the problem. Okay, so let's see. We've got college and high school. High school. All right, so college. We've got 65, our sample proportion was 0.6.65. We can see that. Can you see that? Yeah, I think you can see that. All right, let me write it bigger just in case. Our sample proportion equals 0.65. For high school, our sample proportion equals 0.60. College, we asked, excuse me, 236. For high school, we asked 259. Alright, and that is all we need to know. We're looking at a no difference hypothesis, null hypothesis. So our null hypothesis is going to be, let's see, so proportion 1 minus population proportion 2 equals 0. Alright, so when we take this population proportion minus this population proportion, we get 0. Alright, our alternative hypothesis is going to be proportion 1 minus, not proportion 1, population proportion 1 minus population proportion 2 does not equal 0. Okay, so we in our sample found that the population proportion of college students who knew this information was a little bit higher. It was 65% compared to 60%. But that happens. That may just have been because of the sample we took. That the true population difference is 0, but the sample just happened to be 5% on this one occasion. So let's draw a normal distribution. Let's see, we're going to say the mean of this is going to be population 1 minus population 2 equals 0. So it's a 0 difference. And even if it is 0 difference, we could, on occasion, get numbers that show a really high difference or numbers that show a really low difference. I guess extreme either way. Depends, positive, negative, depends on which one of these you put first. So extreme high difference, extreme low difference. And we're looking at a significance level of, what do we like, 5%? Yep, 0.05. Alright, so significance level 0.05. So that means our critical values are going to separate the upper and lower 2.5%. So that's going to be a 1.96 negative, 1.96 positive. Those are our critical values. So negative 1.96 separates the lower 2.5% from the upper 97.5. Similarly, positive 1.96 separates the upper 2.5% from the lower 97.5. Now, it's possible that we could take random samples of these two populations and get numbers that extreme, but that only happens 2.5% of the time. So if that happens in this case, we're going to say we reject the null and we accept the alternative. Alright, now this normal distribution is our sampling distribution of sample proportion differences. Sampling distribution, sample proportion differences. I like how I abbreviated that. Alright, so we need a standard deviation for that distribution, and we're going to use that to calculate our test statistic. Now remember, when we're calculating the standard deviation, we need pooled proportions, pooled sample proportions, which is just a weighted average of these two. So let's see, pooled. So our proportion pooled is going to equal 236 times 0.65 plus 259 times 0.6, and we're going to divide that by 236 plus 259. All right, and that's going to give us our pooled proportion, which is going to be the first step in getting our standard error. All right, 236.65 times 259, enter 0.6 times plus 236, enter 259 plus divided by. All right, so that's going to equal 0.624. Now I'm going to keep this in my calculator. I'm going to store this in my calculator because this is an important number I need. For now I'm going to call it 62%, but I want that exact number. So I'm going to store that as 1. And then the other thing I'm going to do is I'm going to take 1 minus that, plus, 1 minus, change signs, enter, 1 plus. Alright, and I'm going to store that as well. Okay, so I'm going to call it, for now I'm going to call it 6238, but remember I've got the numbers exactly. So I need the standard deviation, sampling distribution of the sample proportion differences. Alright, and that's going to be my 0.62 times, and I'm using the exact number, I'm just writing for simplicity, I'm writing 0.62, 0.38 divided by 236, is that right? That's what I do. Yeah, divided by the sample sizes, yes. Okay, plus 0.62 times 0.38 divided by 259, 9 square root, that whole thing equals. Alright, good luck. I'll see you on the flip side. So I'm going to do these calculations. You give it a shot as well. So recall 1, enter, recall 2 times 236 divided by. Alright, recall 1, enter, recall 2 times 259 divided by. Add those two together, square root the whole thing. Okay, that's going to equal 0.0436. Alright, I am also going to keep that number in my calculator. So it's about 4.4%. But I'm going to store that number in my calculator so I have it, because I'm going to use that to calculate the test statistic, also known in this case as the z-stat. And that's going to equal the difference, 65% minus 60%. So 0.65 minus 0.60 minus 0, because we're saying there's a no difference. And divide that by our standard error, 0.0436 equals. Alright, so let's see, I store 3, enter, okay. So 0.65, enter 0.6 minus, recall 3 divided by. Alright, and that's going to give me a z-stat of 1.147. Okay? Nice. 1.147. Okay, this is actually something we don't really see very often, because when we teach these types of things, we like to have examples that seem meaningful, so we like z-stats that fall in the rejection region, but it turns out that this one does not. Right? 1.14 falls here, that is inside This does not pass the rejection region. So we do not reject. Do not reject. That's our decision. Let's get the p-value. P-value equals. All right, let's look up 1.147. Now, normally I would go to 1.15, but I happen to remember that the answer in the back of the book, they only went to 1.14. So let's use 1.14. Okay, so the area under the curve for a z-stat of 1.14. And of 1.14 is 12.71%. So 0.1271. P-value equals 0.1271. Now, this is a two-tailed test. There was an equal probability of getting a really high number, equal probability of getting a low number, because all we were saying is that this difference is not 0. So we need to multiply this by 2, and we are going to get, all right, 0.1271, enter 2 times. We're going to get 0.254. All right, let's look in the back of the book. Fingers crossed. 36. Yes. All right, so we look in the back of the book for 36. We've got our pooled sample proportion of 62.4. We've got our standard error of 0.044. You've got our z-stat of 1.4 inside the interval, so we do not reject. And we've got our p-value of 2 times 12.7%, which is going to give us 25.4%. And that is our p-value. And that is greater than our significance level of 5%. And it's quite a bit higher. So this could happen. We could get an answer this extreme 25% of the time. So we're not going to storm into anyone's office and say, I reject your null hypothesis. We are going to fail to reject the null hypothesis. All right, so that's it. I look forward to seeing you in class for class 6. Have a great day.